Okay, thank you very much. So first of all, I'd like to thank the organizers for giving me the opportunity to speak and also for bringing us all to this great and usually sunny place. And I'd also like to thank the following speaker, Gregory Berkolai, who helped me to retrieve the file for this talk after my brand new computer broke down this morning. So my talk is connected to the general topic of semiclassical approach to spectral statistics for chaotic systems, and in particular, I'm talking about very recent papers with Marcel Novaes about endpoint correlation functions, so higher order correlation functions. So this is, of course, related to the random matrix conjecture or BGS conjecture, according to which if we have classically chaotic systems, these display universal statistical properties in their spectra, which are in line with random matrix predictions. And I'm showing the famous picture of three chaotic systems on the right, which all display repulsion between energy levels. So as one example of universal behavior. So if we want to describe spectral statistics quantitatively, then we look at quantities defined through the level density, which is the sum over delta functions located at the energy levels. And then what we are interested in are endpoint correlation functions, which involve products of n different level densities. And I always write the energy argument as E, standard energy, plus some energy increment epsilon. And I'm taking the average level density to 1. And then what do we have to compare to from the point of view of random matrix theory? We have, for systems without time reversal invariance, to compare with the Gaussian unitary ensemble, and there the prediction is a determinant whose entries are sinc functions involving the difference between the energies. It's a determinant of a matrix with sinc functions, and for systems with time reversal invariance, I mean squaring to 1, we have compared to the Gaussian orthogonal ensemble, and the formula for that is a little bit more complicated. I actually won't need the details of it, but it has a Pfaffian form that also involves the sinc functions, but also two different types of integrals. So that's the random matrix predictions, and now we want to make steps towards understanding why individual chaotic systems are faithful to these predictions, and this has been studied a lot for the two-point correlation functions. So I want to give a brief overview also about what was done for the two-point correlation functions. It feels a bit funny with this kind of audience. I'm basically explaining from what many of you your results back to you, but I wanted to include a little bit about it to make it self-contained. So for the two-point correlation function, we can write this as a power series in inverse powers of the difference between the energy increments, and then there are just powers of the inverse increments, and there are so that's non-oscillatory terms, and there are oscillatory terms which have these inverse powers times an oscillatory factor, and the coefficients depend on the symmetry class. So for the unitary case, no time reversal invariance, actually only the leading ones are there. For the case systems with time reversal, we have a whole power series, and if we sum all of them, we get the two-point correlation function, which really goes to 0 for small arguments. So this is capturing level repulsion. And then how can we explain this behavior? So we can use the Gutzwiller trace formula, which writes the level density as the average level density, the Weil term plus a sum over periodic orbit contributions with the primitive period, the stability factor in which I'm absorbing the Maslow phase, and of course the most important thing is the action appearing in the exponent, and there's a real part in front of it, so e to the I and e to the minus I contributions both appear. And then if we plug this into the definition of the two-point correlation function, there will be two factors of this type. So I'm setting the average level density to 1. And the most important contributions actually arise from pairs, from I mean, it's a double sum over periodic orbits, and the important things in the double sum are actually the ones where the actions of the two orbits contribute with opposite sign, and then systematic contributions will arise if because h bar goes to 0, if we can have small action difference. So what we have to look for are correlations between orbits that can give rise to small action differences, and this is also what we will have to look at in a generalized form for the higher order correlation functions. So what one can do is, first of all, the diagonal approximation, so due to Henne and also de Mida and Berry, where you look at identical orbits or time-reversed orbits, and they give the term with 1 over energy difference squared. So I'm here using the energy domain, not the time domain, where we would have the form factor. And the crucial ingredient is the Henne and also Mida sum rule, which contains the prefactors squared, and then summing over that for a given period, and the result is approximated as the period. So that's important to sum over the orbit over the orbits, and then going beyond that, we can look at Sieber-Richter pairs. So the Sieber-Richter pairs involve in position space a crossing with a small angle, and we can narrowly avoid the crossing, or in momentum space. We have here this encounter, and the encounter contains two parts of the orbit traversed with opposite sense of motion, and we can switch connections there and get two orbits that are very similar in their actions. But of course, it depends on time reversal invariance that this is actually possible. So we are, for example, here the bits outside the encounter we call links, and for example, one of the links is time reversed between these two orbits. So then we can go beyond this and generalize this mechanism. So at the next order term, we would have two encounters of this type where two stretches of an orbit come close and we swap connections. So that's the cases on the left. And we also have the possibility to have a more generalized variant of an encounter where three stretches come close, and then if we swap the connections, we get the pictures on the right. So that's the 1 over energy difference to the 4th power term, and some require time reversal invariance, some don't. Those that do require time reversal, those that don't require time reversal invariance give canceling contributions, which actually is needed to show that the diagonal approximation is all that we have for systems without time reversal invariance. And the other case, we can recover this series expansion from it. And so there are combinatorial ways to sum over these diagrams and all further diagrams of a higher order that contribute. And I've stressed here a bit the case where we have a double sum over orbits, which is getting the non-oscillatory contributions. So if we want the oscillatory contributions as well, we have to think a little bit harder on how to approach this. And I mean, there are different ways to deal with this. So there was also work by Borgomoni and Keating, but what we have used in connecting with encounters was the Riemann-Siegel lookalike formula by Berry and Keating, which is morally a way to improve, at least can be interpreted as a way to incorporate more quantum mechanical information into the semi-classical approximation. But this is actually not what I'm going to stress in this talk, because for this talk we are looking at the non-oscillatory contributions. So now the question is how to extend this understanding of spectral statistics from semi-classics to higher order correlation functions. So we use again the trace formula, giving the sum over periodic orbits, and we put it now into all the factors in the higher order correlation function. So that's now a larger multiple sum over periodic orbits. And what is important in the trace formula, we have, okay, I wrote it as a real part of e to the I, so we have e to the I and e to the minus I terms. So if we look at the contributions, for the contributions, we can order the orbits into what we call p orbits, where the action contributes with a positive sign, and what we call q orbits, where the action contributes with a negative sign. And then we relabel the energy increment slightly, so we then use symbols epsilon for the p orbits and eta for the q orbits. So that's slight relabeling to make our life a little bit easier. And then, of course, what we want is the action difference, and this would now be the sum over the p orbits, which contribute positively, minus the sum of the actions of the q orbits, and that ought to be something small. So we need some systematic way of getting this action difference small. And before I talk about that, I want to talk a little bit about bookkeeping in the sum, because that will explain some things I'm going to use later. So we can deal with the energy arguments being slightly different for the level densities by Taylor expanding, using that the derivative of the action is the period. So that was actually also in John's talk yesterday, for example. And we can get the prefactors with the period, so the primitive period, by taking derivatives with respect to the energy that gives this factor extra out of. So we can have the sum without the period and take the derivatives to get the period in. If we argue that the case where the primitive period is not equal to the period is actually not important. And finally, if we plug this in, we will also have average level densities entering. And all the diagrams where we have average level densities entering can be related to lower order correlations. So we can basically use for them what we did if we are given order using what we did for the lower order. So that's for the bookkeeping. But now back to what are the important contributions, so how to get this action difference small. So I'm writing it here again. So we have a similar situation as before, just with more orbits. So what we could have in the diagonal approximation, just pairwise agreement of the orbits, the p orbits with the q orbits, which would then require the numbers being equal. Or we can have p orbits and q orbits differing by changing connections inside counter regions. And that does not require the numbers of orbits to be equal. And we can also have a mix where some q orbits are copied over from p orbits and others are obtained by swapping connections. So that's the possibilities that we have. And I want to show a few pictures for the diagonal approximation. You can easily imagine identical orbits, but here I want to show a few pictures contributing. So for the 3-point correlation function, we have 3 orbits, so that would have to be 1 orbit on one side, let's say it's p orbit, and two q orbits. And the simplest diagram satisfying this is what we like to call the butterfly diagram. So this is one red orbit, but with different connections inside the encounter with the 2 black orbits. And then there's a whole lot of more complicated examples with encounters of 4 stretches, for example, here. So that's 4 stretches coming close and changing connections inside them. And here we have the black orbit on one side, and on the other side the red and the green. And the cumulative action of the red and the green is similar to the black orbit. Or if we go to the 4-point correlation function, we can have 2 orbits on one side and 2 on the other, or 1 on one side and 3 on the other. So this would be here 1 black orbit, but by changing connections, we get the blue, green, and red orbits. And their cumulative action is similar. And here we have 2 black orbits, and changing connections gives the red and the green. So that's also cumulative actions being similar. So that's some examples. And now that I have these examples up, I want to briefly mention something that I don't have time to stress a lot in this talk. So there is a systematic way on enumerating all these diagrams using permutations. So that was actually helpful when there are such long lists to be sure that we didn't miss anything. So you can give numbers to the 2 sides of the encounter, and then we can have one permutation that says how are things connected inside the encounter, so how are the reconnections inside the encounters made. That is some mapping between integers on the 2 sides. And we have a different permutation that is describing the links, the bits outside the encounters, which says, for example, that this end is connected to this end. And then we have a third permutation that is the product that allows us to iterate through the orbit, and it's going, for example, from the start of one encounter to the start of the next encounter, and hence allows to iterate through the periodic orbits. And then the cycle structures of these two permutations contain important information. The one with the encounters, the cycles can be interpreted as corresponding to encounters, and the one corresponding to the full orbits. Every cycle would actually correspond to a full orbit. So that's a way to check, to generate the pairs actually numerically, or check that we didn't overlook any. But now we have to determine the contributions of these. And this is, of course, inspired by the work on the two-point correlation function. So one thing for the semiclassics that we need is the action difference between orbits. And there's a nice way of getting the action difference. If we look at the deviation between two stretches involved in an encounter, we can decompose these deviations into stable component along stable directions and an unstable component, and their product gives the action difference. And then if we have more complicated thing with lots of stretches, there are sums of these products. Then ergodicity is used. So ergodicity is the foundation of the Henne-Osude-Imida sum rule. But we also use ergodicity when counting these encounters, so determining how many of them we have in an orbit. And then if we use these ingredients and calculate, we get a contribution from each link, so each of the bits outside the encounters. So each link belongs to one p orbit and one q orbit. So like this one to the black p orbit and the red q orbit. And we associate to every orbit one of the energy increments. And we can show that each link gives something proportional to the inverse of the difference between the corresponding energy increments. So this is the link factor, the encounter factor. So we get diagrammatic rules also with factors for the encounters. And for the encounters, it's a bit more complicated at first, but one can do have some combinatorial argument to simplify the contributions of the encounters. And the result of that is that the encounter contributions would compensate some of the link factors, namely the link factor is where the link is leading to the first stretch of one of the encounters. So that looks a little bit mysterious at first because it relies on ordering between the encounter stretches. So the argument here goes that we sum over all ways of ordering, assigning labels inside the encounters, and then for each of these ways, the compensation, one of the link factors gets compensated. So this is not making it asymmetric. And then the results that we get after leaving out a proportionality factor and one combinatorial factor that depends on how we precisely define the diagrams. Our result is like this. So this involves the derivatives with respect to energy increments associated to the original orbits, the p orbits and the q orbits, the partner orbits. And this was coming from the step where we try to get the period factors through a derivative. And then we have the link factors, epsilon j minus eta k, but we only take the uncancelled ones because the encounters were leading to cancellation of some. And then we have minus 1 to the power number of encounters. So this is, apart from sort of technical terms that I left out, the result of these contributions. So now what can we do with that? So that's general diagrammatic rules. And they were for the non-oscillatory contributions. So they were just using the trace formula. So for systems with and without time reversal invariance, we can look at the leading diagrams. And we can use this mapping to permutations to be sure that we didn't miss any of them. And then we get agreement of the first leading orders that we checked. So we have lots of tables in the first of these papers. We get agreement with random matrix theory up to the 5-point correlation function for the leading few orders. And the agreement with random matrix theory for the case without time reversal invariance is actually a cancellation because the diagonal of everything related to encounters, because the diagonal approximation should give it all. And then for systems without time reversal invariance, we can actually go a bit further, and we can prove this cancellation exactly for all the orders. And this is based on building a matrix model. So I will talk about the subject of the second of these two papers, and I'll talk about it in more detail afterwards. So this mapping to the matrix model gives the cancellation for the non-time reversal invariant case, leaving the diagonal approximation. And the diagonal approximation we can then actually use from a previous paper with Tao Nagao that was including the oscillatory contributions as well. And there's also a paper of Shukla just for the non-oscillatory ones. So how do we do this matrix model? So I want to discuss a little bit the history of the matrix model. First, Alex actually mentioned the nonlinear sigma model as a way of averaging in random matrix theory, and in the study of the two-point correlation function, we could also describe, have a mapping to this nonlinear sigma model from the semiclassics. And Marcel had a lot of papers where he was deriving matrix models for transport quantities, and the philosophy there, and also in our derivation of a matrix model, was to try to arrange it in a way that we can exactly evaluate the matrix model ourselves. So not by mapping it to something that is then one particular parameterization of random matrix theory matrix models that are evaluated in different ways, but we want to sort of be able to do the integral ourselves. And the philosophy or the derivation of this matrix model otherwise is actually quite similar to the previous cases. So I'm showing the results, which involves the derivatives with respect that I discussed before. Then we take out a coefficient r to the power j plus k, which was the overall numbers of orbits, so the order of the correlation function, and some integrand that I talk about afterwards. But basically, the important thing is an integral over complex matrices Z, just general complex matrices Z, with the Gaussian weight. So there's a Z dagger appearing in the weight twice, so it's Gaussian. And in addition, there are matrices X and Y, and these involve the energy increments for the P orbits and the Q orbits. But there are R copies of each energy increment. So this is and then the integrand actually looks similar to the integration, but with higher powers of Z dagger. So why this form? So basically everything here has an interpretation in terms of orbits. So if we take this integral out of the exponential, we Taylor expand the exponential, we get terms that involve traces of Z dagger outside the exponential, but then a Gaussian integral. So that's Gaussian integrals of stuff that is just linear products of Z and Z dagger. And that is kind of tailor-made for the Wick theorem, so to look at contractions of the integration variables, so the matrices Z. So we look at contractions between these matrices. And it turns out that the contraction lines can be associated to the links, so the pieces outside the encounters. And this we can, for example, one thing that we have to check to make sure that that's true is that the contributions are the same. And if we have such a contraction line, then the contracted elements, if we write everything out in indices, will actually have indices. And if we identify the indices with the indices of the periodic orbits, and we look at what the X and the Y were in the measure, then we get contributions that are like the link factors, so the epsilon j minus eta k inverse. So that's as it should be. And then the traces that we are integrating over are analogous to the encounters. So that's actually sum over powers. So we would identify each Z dagger with one encounter stretch. And so the power of that means sort of the order of the encounter, and that's what we identified with the beginning of the encounter stretch and the Z dagger with the end of the encounter stretch. And then what we can actually see that there is a nice relation to how the encounters properly look if you write the matrix product out with the indices, and if you compare to how you would draw an encounter. If you would draw an encounter, you have the 3 stretches in the p orbit and 3 stretches by dashed lines in the q orbit, and the dashed lines are connected differently than the full lines. And if I write always indices k for the ends of the encounter stretches that go along the dashed lines, and indices j according to the full lines, then that actually tells us which orbits do the ends of the encounters belong to. And then what we get from, so that's sort of one way of getting this picture from drawing encounter and looking which orbits do things belong to. But a completely analogous way that gets to the same picture is to just write out these matrix products with indices, and that leads to the same identification with indices. So this is describing well the encounters. And I mean, I don't want to go through all the steps of deriving it. I mean, one thing I should maybe hint is the r to the power j plus k coefficient. We want to make sure that we have the right number of orbits contributing to the diagram, and one can check that every orbit leads to a power r, which is due to the fact that one can show that all indices related to that orbit actually have to coincide. So there are, and then because we are repeating each of the epsilon r times, this leads to an r-fold degeneracy per periodic orbit in the contribution. So that's establishing a matrix model, and then we can just evaluate the matrix model. So I'm skipping a bit the steps for that. I mean, it was an Zuber integral somewhere, and this is one form in which one can write the result. And then we have to show that we would, so that's just the integrals done, but still the derivatives and the isolating the coefficient needs to happen. So how do we do that? So it actually turns out that the whole result is of the encounter contributions is then 0, because one can show that every single term here is either vanishing due to the derivatives giving 0, because it was not depending on one of the parameters, or it vanishes because it has the wrong power in r, and hence the r to the power j plus k coefficient is 0. So that is sort of a way of showing that all the off-diagonal contributions cancel for term reversal, for non-time reversal invariant systems, for non-time reversal invariant systems. Okay, so to conclude, we've seen that endpoint correlation functions of chaotic systems can be written as multiple sums over periodic orbits, and we could evaluate the relevant contributions to these multiple sums by looking at orbits that are identical, so generalizing the diagonal approximation, all that differ in encounters. And then we saw, as far as we could get, this agreement with random matrix theory, and this was for the non-oscillatory terms that we looked at. And then in the case with time reversal invariance, we had just the check of the leading, I mean, a couple of leading orders, so not just the first up to the 5-point correlation function. And for systems without time reversal invariance, we could do this individual check, but we also had a general argument why everything related to encounters gives a canceling contribution. Okay, so that's